Alright, hi everyone, welcome to my YouTube channel, City of Elections. So in this video, we are going to do this. We are taking it from, we are going to do this, okay? Taylor series. But we are going to take it from this point right here. Now looking at this solution we have here can be referred to as the exact solution of what we had when we talked about terminal velocity, when we calculated that from this point. Okay, trying to calculate the terminal velocity of the parachutist. So of course, if you've not seen this video, the video will talk about the simple math model and from simple to complex math model. Please check out that video. Okay, so it's from that point we calculated and we derived the solution for that. Okay, so this equation 10 is called analytic or exact solution. Now, and that's called exact because it satisfies the original differential equation. Okay, you know we had equation 9 here. Where is that? Yeah, no, not this. Yeah, this one, equation 9. So we solved from this point to get equation 10. So it satisfies the original differential equation. But the thing is this, we do not always have the exact solution because there are mathematical models that cannot be solved exactly. Okay, and don't bother that much if you don't really understand what I'm saying now. But the main point is this guy satisfies the original differential equation, so it's the exact solution. But there are mathematical models whereby we cannot get the exact solution like this. We cannot get what satisfies the differential equation. And of course, the differential equation I'm talking about that is being satisfied is this one, equation 9. Okay, so yeah, so in that case where we have math models where the differential equation cannot be we cannot get the exact solution, what we'll do, what should we do? This is what we are going to do. We are going to develop a numerical solution for it. Okay, so what I'm saying is that in many of those cases, or the cases where you cannot get the exact solution, the alternative is to develop a numerical solution that approximates the exact solution. That is where we have numerical techniques for solving ordinary differential equation. Okay, so of course the definition just talk about or just points out what I've been saying so far, which is numerical solutions are those in which a mathematical problem is reformulated so it can be solved by arithmetic operations. So since we cannot get an exact solution, we have to reformulate it in a way we can use arithmetic operations to solve it. And there are 5 techniques listed here, and we have that as: 1 is the Taylor series method, 2 is the Picard's method, Euler's method, Rom-Chukuta's method, Euler's modified method. Okay, so yeah, those are the methods. So this video we are going to just focus on the first method, which is Taylor series. Okay, so now usually I'm supposed to start with this example step by step and you follow alongside, but I've made this video like twice, so to write the whole stuff again is like, so what I will do, I will explain all I've written, and then where I need to write out the points, I will do that for you. So this first thing to note or bear in mind that when using the Taylor series method, we need to know the Taylor series first. So this here is our Taylor series, and what it actually means is the value of y, of course a function of x. This first here is when n is 0. When n is 0, it means y is not differentiated, so it's just y, which is what we have here. y. Then this is x minus 0 bracket 10 raised to the power 0. Anything raised to the power of 0 is what? 1. So everything here is 1. That means this is what I'm talking about. That means this is just y, meaning 0 on top here. It means we are not differentiating it, it's just y. But this 0 on top here, it means everything gets raised to the power of 0, meaning everything here will be what? 1. So 1 times y is the same y. Then n factorial, 0 factorial is what? 1. So this thing remains like this. Then the next term, when here is 1, it means the first derivative of y. You're going to take the first derivative of y. Then of course when this is raised to the power of 1, we'll now have this written here. We have it there. Then n1 factorial is of course 1. So this divided by 1, it remains the same. Then the next term here will be 2, which means the second derivative of y. That's y prime prime. Then when here is 2, of course we have a raised to the power of 2. Then 2 factorial, 2 factorial, and so on, just like that. So that's how the Taylor series looks like, so on. Okay, so let's take an example. We have a differential equation here, this. So we are going to solve this differential. We have a differential equation here, which is this guy. Okay, we are going to solve this differential equation using Taylor series method. Okay, so the idea is this. Check out this hint here. This is the idea. Find each derivative of the given differential equation. Substitute the values of x and y at each derivative. Substitute the solution of each derivative into the Taylor series. Straightforward. Look at what that means. So this is the first derivative, right? And this is y, and this is x0. So when we are not taking any derivative, y here will be what? 1. At the first derivative, dy dx, which is y prime and dy dx is the same thing. D squared y and dx squared and y prime prime is the same thing. Okay, that is dy dx is the same as y prime. Okay, so put this aside. Alright, so at just y0 we'll put 1 there. Then at dy dx we'll put this thing here, but we don't need all this, like everything here to be at this point. What we need is to have the value of dy dx, meaning what is x, you put 0, what is y, you put 1, and then you get the value. So look at it here, dy dx, look at it here, dy dx. So 3 multiplied by x is what? 0, you put the 0, plus y squared, y is what? 1, so you have 1 squared. You solve it and you have 1 here, meaning dy dx is the same thing as 1. So here we have y prime, we are going to put 1 in this equation. Okay, I hope that's clear. So in essence, we need to find y prime, which is dy dx. We need to find d squared y dx squared, which is y prime prime, and y prime prime prime. Just find them, like calculate them and put in the values. So what we have done now, we have for dy dx, which is this point. So let's go for this, and so on. Since we have dy dx, now let's go to the next thing, which will be what? D squared y dx squared, meaning you are to differentiate this guy again. So 3x, when you differentiate this with respect to x, you have 3. When you differentiate this with respect to x, now, but there is no x term here, right? So therefore you will differentiate this. Of course it will be 2y, but because there is no x term, it will be an implicit differentiation, meaning after differentiating it, you have to place dy dx. So this will be 2y. Look at it, 2y. But since there is no x term, you will now write dy dx. Okay, So this is our equation 2. Now to get the value, that's the number for the second derivative, this is the equation for second derivative. What is the number? What is the answer? So you put in your values. 3 is 3, 2 is 2, y is what? Look at it, y is 1. You put the 1 here. Dy dx is what? We have gotten dy dx as what? 1. So you put the 1 here. Then of course this multiplied by this here is 2. 2 times this 2 times this 2. 2 plus 3, 5. So we now have values for the second derivative. Okay, now we'll go for third derivative. To get third derivative, just differentiate your second derivative, you get third derivative. So differentiating second derivative, of course, when you differentiate a constant, 0, so that guy is off. Okay, so we'll come to this side, this second part now, to differentiate this. Now if you look at this, we have two terms here. We have this we have this, oh boy, we have this and we have this. Okay, so we are going to differentiate this just like we did at first, but the thing is, there's a rule called the product rule, because this term is multiplying this term. So in product rule, you do this. Product rule, let's say the first term there is u, the second term is v. Okay, u and v. So the idea of product rule, oh I have it here, thank God. So the idea of product rule is that the first term you will hold it, and then you differentiate the second term with respect to x, or you just differentiate the second term. Then you now say plus the term you differentiated, this time you will hold it your second time, and the term you held the first time you will now differentiate it. Meaning we are going to have at this point now, so we differentiate this one and we hold this one. Okay, I think what I did there, I held this one. I held this one first, what I did. So let's hold this one, meaning leave it as it is. So 2y, look at it here, 2y. Then dx squared, dx, if you differentiate dy dx, of course it will be the second derivative. We are going to have d squared y dx squared, which is this, plus, now I want to take the second term now. Now this is the one we are going to keep now. So keep dy dx, look at it, dy dx. Now let's differentiate this now. So if you differentiate 2y, you will get 2. But because you are differentiating with respect to x and there is no x term here, you have to put what? Dy dx. So that's how we have this part here. Of course, in case you are not so clear with anything, pause the video, try to maybe take it back, rewind the video, and then step by step you get it. Okay, so with that being said, the next thing we just simplify it. So this is 2y d squared y dx squared, which is what we have here. And then for this multiply this, of course it will be dy over dx squared. Okay, all squared. So all we have to do now is just put in the values. 2, what is y? We recall that y is 1, which is this. Then dx, d squared x over dx squared, this is the answer here, 5, that's the 5, plus dy dx is what? 1 raised to the power of 2, which is what we have here, 1 raised to the power of 2. So when you simplify that, you have this. Okay, so now let's take the last derivative. We don't try. So we're going to differentiate this guy. Either we differentiate this or we differentiate this, because they are the same thing. We just simplified one of them, and I think we can just differentiate this part. So of course, product rule here again. Okay, so we hold this first, we hold 2y, which is this 2y, and then we differentiate this. Of course, the 2 will become 3, here will become 3, which is this. Perfect. Plus, now we hold these parts, look at it here, and we differentiate these parts. So when you differentiate this, you have 2, but because there's no x term, you will now put dy dx, which is this part. Good. Plus, look at your plus sign here, plus. You differentiate this. Now remember chain rule differentiation, where you differentiate what you have inside and then use it to multiply outside, while you also differentiate everything like this. So let's differentiate everything like this. Okay, if you differentiate this stuff here, what you have is this 2. Of course, this 2 will come down and multiply this, it will give you 4, and you minus 1 from here. Of course, here will just be 1, so you have 4, and then you have this dy dx will also be there, 4 dy dx. Meanwhile, you also differentiate what you have inside and use it to multiply the result. So if you differentiate this, it will be d squared y over dx squared. So use that thing to multiply this, which is this now. So differentiate the inside, you have d squared y dx squared. Look at it. Use it to multiply, differentiating everything here. Differentiate everything here as a particular term. You have 2 multiply this as 4 dy dx. Look at it, 4 dy dx. Good. Of course, if you have any question, leave it in the comment section, or any contribution or anything like that, or maybe I missed out something, or something is missing, or something is up, just okay, comment. All right, now so we just put in the terms. Y of course is 1. Our third derivative is 12. Let's check it out to be sure. Yeah, third derivative is 12 plus second derivative is 5. Am I sure? Yes, second derivative is 5. Yes, it's 5. Then this 2, look at it here, 2. First derivative is 1. 4, look at the 4 here. First derivative is 1, second derivative is 5, and you just do the math. This will give you 24, this will give you 10, and this will give you 20. You sum that up, give you 54 as your first derivative. Now all we have to do is to go back to our Taylor series and plug in the values. So of course, when at y not being differentiated, y is 1. This x, look at the x here. Of course, x0 is 0. x0 is 0. Look at it here, x0 is 0. Beautiful. So x0 is 0. y1, that's the first derivative of y. I mean y prime is 1. We got that as 1. Plus, go to the next part. X there, x0 is 0. Use to power 2, power 2. 2 factorial is 2. Then the second derivative of y is 5. You can check up and confirm that. Plus x, yeah, x minus x0 is 0. Use power 3, use power 3. Third derivative is what? 12. 3 factorial is what? 6, because 3 factorial is 3 times 2 times 1, and that's 6. Plus. So the pattern goes on like that. So x minus x0, this time here will be 4, and here is what? 4 factorial, that is 4 times 3 times 2 times 1, and that's 24, multiplied by first derivative of y is 54. Okay, so we just now the question is, what is y when x equals 0.1? I think we have that in the question. Okay, I should have included that, because that's what part of the equation is in my notes. Okay, I think it should be in your notes too. So the question is find y when x equals 0.1. Yeah, that's the question. So now this we have here, this now will give us an approximate value of y, this expression. So all we have to do, where we see x, we put 0.1. So 1 plus x 0.1. Of course, 0.1 minus 0 is the same 0.1. 1 multiplies 0.1, the same 1. So plus x to 0.1 raised to power 2. Of course, this 0 is out, okay? Divided by 2, multiplied by 5. Next, plus x, 0.1 raised to the power 3, divided by 6, multiplied by 12. Okay? And then, plus sign, of course, x raised to the power 4, x to the power 4, divided by 24, multiplied by 54, multiplied by 54. So, once you just do that, if you want to use your calculator, if you want to use calculator to save your time, you can do that sharp, and you have this as your answer. So this is using Taylor series to get the approximate value of y when x is 0.1. Okay, so I really hope this video helps somehow in a way. So comment in order for you to get clarity. Okay, so yeah, like, share, subscribe, and I'll see you in the next video. Thanks a lot for watching, and bye for now.